All right, let's talk about the single most important first step to solving basically any differential equation you're ever going to face. Seriously, it's a simple little trick that's going to save you a ton of time and, honestly, a lot of headaches. Let's jump right in.
You know the feeling, right? You're staring at this monster of an equation, and your brain just freezes. The first instinct is to just start doing algebra. You try one thing, it doesn't work. You try another, and you're just digging yourself into a deeper hole. It's frustrating, it's a huge waste of time, and it's just a terrible way to solve problems.
But there is a much better way. So here's our game plan for this explainer. We're going to talk about the core problem. I'll reveal the classify first secret. We'll walk through the 6 main types of equations you absolutely need to know, and then I'll show you exactly why this method is a total game changer.
Okay, so first up, let's define the actual problem. The biggest challenge with differential equations a lot of the time isn't even the calculus or the algebra. Nope, it's figuring out which tool to pull out of the toolbox. You have all these different methods, but which one is the right one for the equation staring you in the face?
Just guessing or trying to brute force it, that's a recipe for disaster. You end up wasting so much time on exams just trying random things, which, by the way, is where all those little sign errors and algebra mistakes creep in. It's not just slow, it's a really bad strategy.
So what is this secret, this better way? Well, it's a powerful little shortcut that unlocks the correct path instantly. The whole idea is to change your first question. Instead of asking, how do I solve this, you need to start by asking, wait a minute, what is this?
And here it is. This is the mantra. If you take one thing away from this, let it be this quote right here. Classify before you compute. Taking just a few seconds to identify the type of equation you have isn't wasting time. It's the best investment you can make because it tells you the exact method to use every single time.
The process itself is so simple and logical. You just look at the equation, ask yourself a couple of key questions, match it to one of the known types, and boom. Just like that, you know exactly what to do. It turns a wild guessing game into a clear 4-step process. All right, let's open up that diagnostic toolkit. We're going to go through the 6 essential classifications that you really need to have in your back pocket. I promise you, if you master spotting these 6 types, you'll be able to handle almost any first or second order DE they throw at you.
First up, the most straightforward one of the bunch, the separable equation. The name really says it all. If you can use algebra to get all the y stuff with the dy on one side and all the x stuff with the dx on the other, you're good to go. You know, something like dy dx equals x squared times y. That's a classic separable.
So your diagnostic path is super simple. The very first question you should always ask yourself is, can I separate the variables? If the answer is yes, you classify it as separable, and you immediately know your method is direct integration. Done. Next problem.
Okay, next in our toolkit is a really common one, the linear first-order equation. This one is all about pattern recognition. You are literally looking for this exact structure. You've got your dy dx, then you've got some function of x, let's call it p of x times y, and that's all equal to some other function of x, q of x.
And this example shows you the power of this perfectly. Look at dy dx plus 3y equals 6. Does it match that standard form? Absolutely. Your p of x is just the number 3, and your q of x is 6. You don't have to guess. You know with 100% certainty that this is linear first order, and the tool for that is the integrating factor. Moving on, we've got exact equations. These guys have a very specific look to them, this mdx plus ndy equals 0 format. So you might see something like 2xy dx plus x squared minus 1dy equals 0. But here's a word of warning. Just because it looks like 1 doesn't mean it is 1. It has to pass a crucial test. So this is a 2-step diagnosis. First, does it have that mdx plus ndy form? If it does, your next step is to run the exactness test. You check if the partial derivative of m with respect to y is equal to the partial of n with respect to x. If they match, then you can officially classify it as exact, and your job is to find the original potential function it came from. All right, our 4th type is the homogeneous equation. Now, these can be a little bit tricky to spot, but the big giveaway is that you can rewrite the whole thing as dy over dx equals some function of the ratio y over x. Think dy over dx equals x plus y over x. If you see that, the magic bullet is the substitution y equals v times x. That little trick will transform the whole thing into a separable equation, which you already know how to beat. Next up, the Bernoulli equation.
I like to think of this one as the sneaky cousin of the linear equation. It looks almost identical to the linear form, but it's got this one extra piece on the right-hand side, a y raised to some power n. That single term, like the y squared in dy dx plus y over x equals x times y squared, is the only difference, and it's your clue.
So your diagnostic question is simple. Does this look linear, except for that extra y to the n thingy? If the answer is yes, you classify it as Bernoulli. And here's the really cool part. The method is to use a substitution that transforms it back into a linear equation, which is a problem you already have the tool for.
And finally, we have higher-order equations with constant coefficients. You're looking for two things here. First, are there second derivatives, third derivatives, y double prime or higher? And second, this is just as important, are the coefficients in front of the y terms just plain old numbers, not functions of x? A perfect example is y double prime plus 5y prime plus 6y equals 0.
The diagnostic path here is crystal clear. Are there higher-order derivatives? Yes. Are the coefficients constant numbers? Yes. If you can answer yes to both, you classify it, and your go-to method is the characteristic equation. This is the one you use all the time for things like springs, circuits, and vibrations.
So, we've walked through the whole toolkit. Now, let's talk about the payoff. Why is taking those few extra seconds to classify the equation first so unbelievably important? I mean, what's really in it for you?
Well, the benefits are huge. First, it's going to make you way faster on exams. By picking the right method from the get-go, you cut out all that wasted time and dramatically reduce your chances of making a dumb algebra mistake. But more than that, it builds a real intuition for what these equations mean and how they model the real world. This isn't just a test-taking trick. This is how professional engineers actually think. So let's bring it back to our mantra one last time, because it really is the heart of all of this. Classify before you compute. This single tiny shift in your approach is the foundation for solving these things correctly and confidently. Ultimately, what this method gives you is a total transformation. It takes that feeling of being lost, that confusion when you first see a complicated DE, and it replaces it with the confidence of knowing exactly where to start and the precise path you need to follow to get to the answer. You now have the diagnostic toolkit. You have the keys to unlock these equations efficiently, accurately, and without all the stress. So the only question left is, which differential equation are you going to go unlock next?